It's a really great privilege for me to introduce Nigel Packham, who I've known for a couple of years now. Nigel is the manager of the Flight Safety Office in the Johnson Space Centre Safety and Mission Assurance Directorate, where he's the Associate Director. He is a Deputy Technical Lead for Life Support Systems for NASA's Engineering and Safety Centre. Maybe best known for being the Project Manager in an effort that culminated in a release of the Columbia Crew Survival Investigation Report. You may remember that disaster in 2003. Nigel is very familiar with simulation. He's actually previously been commander of a 4-person crew and spent 91 days inside a 6-metre diameter chamber to demonstrate the capabilities of advanced systems for air, water and waste recovery for long duration missions. It might take a lot of paperwork to get that approved in the NHS or HSC. So Nigel will be making his presentation now and afterwards be addressing us via a Q&A. And I have to ask everyone who wishes to ask a question, please wait for a roving microphone. We have people who will run to you with their microphones. So without further ado, I'll hand over to Nigel, who you can see is in NASA's Johnson Space Centre in Houston. Welcome, Nigel.
Well, good evening, Martin, and good evening, delegates to the ASPE conference. For Dr. Barber, it's my honor to be here and to address your delegates from Houston, from the Johnson Space Center, and from where I'm sitting, which is literally about 200 yards from the very historic Mission Control Center, from where the infamous words were spoken, the first words from the surface of the moon: Houston, tranquility base here, the Eagle has landed. So Houston was literally the first word to be spoken from the surface of the moon. So you might be wondering, why would somebody be sitting in a conference room at NASA in Houston, Texas, talking to such an austere group of folks at the ASPE conference? Doesn't seem that there will be that much of a connection between human spaceflight and what you're talking about over the next few days. But in fact, I'm hoping over the next 30 or 40 minutes or so that I'll make that connection for you strongly, and hopefully open up some further dialogue with some of your delegates. So if we could, I'm going to start out with a video first of all that was made by the crew of the last space shuttle flight that flew back in 2011. The 4-person crew spent about 15 days on orbit, docked at the International Space Station. But what I want to show you is when you look at this video, what you'll see is that about T-minus 31 seconds, or 31 seconds before the actual launch of the shuttle, there was a failure. And what happened in the next 31 seconds leading up to launch of that space shuttle was a very rapid recovery from that failure, which had been simulated many, many times. And so with a very, very short launch window, the launch window was only 5 minutes long, the flight control team here in Houston, working with the folks down at Kennedy Space Center in Florida, were able to actually clear that vehicle for launch. And okay, so hopefully you got an idea of what human spaceflight is all about. Actually, what you should also know is that the third person you saw getting on the shuttle there in the orange suit, it was actually is currently my boss. He's also the person, and if you saw the shot that's taken from inside the cockpit looking backwards, the one person that has the broadest smile across his looks like he's the Cheshire Cat. But I really didn't show you that just for fun. I also wanted to show it to you because a lot of people ask me today whether human spaceflight is safe. That's literally the words that they use. Is it safe? And I think when you see that video, especially when the main engines light up and when the solid rocket motors light up, with 7 million pounds of thrust pushing that shuttle uphill, that certainly the question, is it safe, really doesn't seem to be the right question at all. So if we can go to the next chart, please. So what you should now be seeing is our 4 photographs. So on the top left is a question that we ask of other industries and academics. So the question, is it safe? Well, the left-hand side of that picture shows Deepwater Horizon. So back in the 2010 timeframe, the resulting explosion in the Gulf of Mexico resulted in the loss of 11 crew members. Similarly, on the right-hand side there, you'll see the Space Shuttle Columbia coming back in 2003, resulting in the loss of all 7 crew members. And I should note 7 of them are my very good friends. So go to the next chart. You could say the same thing about commercial aviation, really. Although it's inherently much more safe, the question is still out there, is it safe? Well, back in 1989, in July 1989, United Flight 232 took off from Denver heading towards Chicago in a DC-10 aircraft. The DC-10 is shown on the top left-hand side there. Has 3 engines on it, the 2 engines underneath the wing, and then the tail engine. Well, midway into the flight, that tail engine basically disintegrated, and the disintegration took out all of the hydraulic systems on that plane. Well, only through the remarkable flying of the 2 pilots and an additional pilot that was in transit could they actually fly that plane, attempted to fly that plane back to a safe landing. They actually landed in Sioux City, Iowa, as a crash landing, but 185 people survived that crash landing and 111 fatalities. So again, the question, is it safe, really, it doesn't seem to make sense in that situation either. So let's look at the chemical industry. This is the Union Carbide plant in Bhopal, India, when in 1984, 40 tons of methyl isocyanate material were released into the atmosphere, resulting in an estimated 25,000 fatalities. And in fact, I have it on good information that actually is much greater than 25,000, probably more like 100,000 fatalities back in 1984. In your world, you may also get the question, is it safe? So let's take a real-life example. So in my situation on board the International Space Station, we've had this real-life scenario actually take place. So a critical circulation pump in the thermal control system is malfunctioning. It's being required to deliver 1.5 liters per minute at 950 millimeters of mercury, but it's actually only delivering about a half that and at about a quarter of the pressure. So a thermal control system engineer might ask himself the question, how long has it been going on? So what is the pump's history? It's been a gradual decline over several months. Is there any real-time X-ray? And if it does, it shows potential leakage around both the inlet and outlet valve seats. So what's the effect on downstream systems? So we're getting a lower cooling capacity in the system. It could reach a critical point in 6 months at that present rate of decay, leading to shutdown of that life support system. So next chart shows what are the options. So that thermal control systems engineer might ask him, what are the options that I have? I could remove and replace the pump. Unfortunately, there's no pump available because it's no longer manufactured. It'll take 12 months and $5 million to build a new one from scratch. I could remove and replace the valve seals. That assumes that the seal integrity is the only contributing factor. And could an astronaut be trained to perform that procedure in the zero-gravity environment of the International Space Station? I could do nothing to the pump, but I could provide secondary cooling to the life support system until the replacement pump can be manufactured. We've got a secondary cooling system on orbit, relatively simple operation. We have an astronaut on board that has experience with that pump, and we can even do refresher-type training available through the just-in-time training. Or we could do nothing. The space station itself has already exceeded operation expectations, and we could evacuate and terminate the program. The main thing I want to stress here, these are all risk versus risk trades, apart from the last one, which obviously is doing nothing, in which case the expected result is going to be termination of the program. So what about in the medical equivalent? Next chart. So let's say that an 82-year-old male patient presents to you with symptoms of circulatory problems and they are hypotensive. The physician might ask several questions, such as how long has it been going on? What is the patient's history? What other symptoms are associated with a potential diagnosis? And what diagnostic tools are available? Is there ECG? Is there angiography? And again, I am not a physician, so please excuse my limited diagnostic tools. So on the next chart, what are the options to the physician and the patient? option A, B, and C, or is there an option which says do nothing? Again, I would put it to you that these are all risk versus risk trades. So there's some commonality between the world that you live in and the world that I inhabit here at NASA's Johnson Space Center. So if we talk about risk, let's look at the next question. So let's go back to that is it safe question. Is that really the right one? Or is it safe enough? Is that a more appropriate question? And more over here, we're actually hearing, prove to me that it's unsafe. In other words, the procedure I'm about to undergo is unsafe versus to prove to me that it's safe, which is really the right question to be asking from the safety community. But in terms of being able to answer that question, you need to understand the management of risk. So in order to manage the risk, you have to know what it is, identify the causes of that risk, determine the likelihood, which is the probability, and the consequence, which could be, in our case, loss of life, loss of our mission, loss of financial assets, if the event were to actually come to fruition. Our next step would be then to mitigate the risk wherever we could, but in the end, accept any residual risk. And the good question there is, who accepts that residual risk? In my world, as the residual risk increases, the level of management has to increase that accepts that risk. And the ultimate risk taker is actually the astronaut that climbs on board that space shuttle or that next space vehicle. In your world, that might actually be the patient. Let's talk about a real part of risk. So let's talk about the space shuttle again. The first shuttle flight happened in 1981. And at the time, we estimated the risk to losing that crew, which we called LOC, we calculated it to be between 1 in 1,000 to 1 in 10,000. So in other words, we calculated that there was a 1 in 1,000 to 1 in 10,000 chance that that crew might not come home. So that was based on all the tools that we had available at the time. So if we fast forward, though, another 30 years to the end of the shuttle program, to 1981, and we now use the tools that we have available and all the experience that we've gained over those 30 years, I wonder if you could understand what the actual risk of losing that first crew was. So I'm going to ask you to put your hands up, and I don't want you to go to the next chart yet, please. But if you think it was actually riskier than 1 in 1,000, that means it would be 1 in, let's say, 500. Put your hands up if you think it was riskier than 1 in 1,000. So that's about a tenth of you. So how many of you think it might have been less risky? In other words, greater than 1 in 1,000. Okay. The reluctant people that don't put their hands up, I'll guess you're somewhere in the middle. So if you go to the next chart, the actual risk of losing that crew for the first shuttle flight was 1 in 12. That means we had a 1 in 12 chance that that first crew was not coming home. That first crew consisted of Captain John Young, God rest his soul, and Bob Crippen. I knew Captain Young for a lot of his NASA career, and the person that walked on the moon, I think even if he had known that the risk of him not making it back was 1 in 12, I think even John Young would have puckered just a little bit. But what it goes to show you is that your understanding of risk, in this case to the crew, in your case to the patient, is dependent wholly on the tools and data that you have available to you at the time you make that risk decision and that risk calculation. All right. So next chart, if you would. So we're going to quiz you a little bit here. So the question I have for you is, how many fatalities in human spaceflight history have there been? And I'm making it easy for you. It's even multiple choice. So I'll give you 3, 17, 21, 18, and 10. I'll give you a couple of seconds to think about what your answer might be, and then I'm going to walk you through it. Okay. So, fatalities in human spaceflight. If we go back to 1961, next chart. This is Apollo 1, or some people over here, we actually use the terminology AS-204, where 3 Apollo crew members on the ground were performing a test in a capsule that actually would have taken them to the moon. But Apollo 1 unfortunately had a fire, and we lost 3 of our greatest assets, our 3 crew members. So that would be 3 in 1961. You may remember the Space Shuttle Challenger. So next chart, please. Space Shuttle Challenger in 1986, we lost 7 crew members there, including the first teacher in space. So that's another 7 crew members. Next chart, please. 2003, Columbia, February the 1st of 2003, disintegrated on entry back into Earth's atmosphere. So how many of you said, if you add those up, 7 plus 7 is 14 plus 3 would be 17. How many? Put your hands up if you said 17. Oh, we have 1 or 2 or 3. Okay. So let's go back to the original question. Can you go back up about 3 slides, please? To that one. Look at the question again. That is, how many fatalities have there been in human spaceflight? And I think I gleaned from Dr. Duffy's introduction that not all of you are from Belfast, and some of you may be from other parts of the globe. So let's include other parts of the globe and go forward 4 slides, please. So back in 1967, this is Soyuz 1. This is a Soyuz capsule that was launched from Baikonur Cosmodrome in Soviet Union at the time. When this flight actually launched, it was launched ahead of schedule, and that schedule was accelerated only to coincide with the celebration of a political anniversary. So it was actually launched ahead of its time. They knew it wasn't ready to fly, but they flew it anyway. The pilot of that Soyuz spacecraft was Komarov, and Commander Komarov launched and successfully made it to orbit. But as had been predicted by some on the ground, they found out that his parachutes that slow the capsule down were not going to function when he came back into land. They told him that on orbit, that his chutes were not going to open and that he was going to perish upon entry. They brought his wife into the Mission Control Center in Korolyov, Moscow, just outside of Moscow, actually. And after a brief chat with his wife, they deorbited, and in fact, the Soyuz capsule plowed into the steppes of Russia at terminal velocity, obviously resulting in 1 fatality. Back in 1967. If I told you that the original pilot of that particular flight was not Komarov, but was another very famous Russian cosmonaut, I wonder if you might know who that might be. But obviously I can't look at you in the face, unfortunately. I'm looking from behind you. But the pilot of that first Soyuz flight was supposed to be Yuri Gagarin, the first man in space. Let's go to the next chart. So there's one fatality there. Back in 1971, this is Soyuz 11. This was a successful chute opening and a successful descent and landing of the Soyuz 11 spacecraft, and that is the intact Soyuz spacecraft that landed on the steppes of Russia back in 1967. I'm sorry, 1971. The crew that are around that Soyuz capsule, even though the photograph is in black and white, I'll show you one in a few minutes that is a modern day version of this. When they opened the hatch to that Soyuz spacecraft, they actually found 3 dead cosmonauts. During the entry phase of the mission, a hole had developed in the capsule which could have been actually stopped. That leak could have been stopped by turning a multi-turn valve. The 3 crew members inside managed to get that valve closed 5 turns of the 10. And not wearing spacesuits, they actually ended up perishing from hypoxia. They did perform CPR on the ground at in Russia, but unfortunately those 3 crew members perished also. So the total actually would have been 21. Did anyone actually think it was 21? Let's do it by show of hands. A few of you. Okay. So if we go to the next chart, if you compare that black and white photograph in 1971 with the photograph of the same Soyuz spacecraft that landed in 2008, apart from the fact that there is a color photograph there, the spacecraft itself is almost identical. This was a successful landing, and the 3 crew members in this particular Soyuz landing were actually extricated from the Soyuz capsule and were fine. I'd like to draw your attention to the helicopter in the back far right of the picture. In the photograph in 1971, that helicopter is in black and white, but the same picture in 2008, I will point out that that is not only the same type of helicopter, it is confirmed that that is actually the same helicopter some almost 40 years later. One thing to know about the Soviets is that they actually, and the Soviets and now our Russian colleagues, is that they make very good use of the assets that they have available to them at any one time. So in this particular case, that helicopter is still flying. Some of the American astronauts that landed and were transported by that helicopter said that that was the most dangerous part of their mission. All right. If we go to the next chart, well, the next chart will show you the actual number was 21. And then finally, and the next chart, if you will go to that, I'd like to spend a little bit of time on this chart. It's very difficult for you to read, but I will explain to you exactly what we see. If you felt that those 5 events that caused the loss of life of 21 crew members over that period of time were the only events in human spaceflight history that had the potential to either cause harm to a crew or kill that crew, you'd be very wrong. Every box that you see on that chart up there represents one such event. The yellow boxes with red borders do represent the events which included fatalities, but every other box there had the potential to either kill the crew or cause harm and debilitating injury to that crew. And the way you read this is from the left-hand side, the green line going up is the ascent phase, that is after launch, going up into space. The blue line going across the middle is Earth orbit. If these were Apollo missions or missions out to the moon, the line going out to the moon and then down to the surface of the moon, back up from the surface of the moon into lunar orbit, back to Earth orbit, the entry phase, the descent phase, and the landing phase. So we have had incidents occur in every single one of these phases that have actually either had the potential to kill the crew. This is a public-facing document, so this chart, if you actually were to Google significant incidents and close calls in human spaceflight, you will get this chart. And today's chart is actually interactive, so for every box there, you can actually click on that box, and it will take you to more information about that particular event. In the time that I've been here at NASA's Johnson Space Center, which goes back to 1991, and this chart depicts events that happened way before that. I've had people come to me and ask me, why do we actually tell the world about the bad things that have happened at NASA? Well, it's because of the business that I'm in. I'm in a government position. I can actually tell the outside world exactly what has happened in our business that has led to the loss of crew members or the harming of crew members. I've tried to tell this story to the oil and gas industry, to the commercial aviation industry, to the medical industry even. There is very little incentive for those industries, especially ones like oil and gas and commercial aviation, to actually draw a parallel type analysis to the one that I just showed you, where events that have had the potential to cause harm to personnel or actually kill personnel in their particular industries, there's really very little incentive to do that because of the bottom line, and that being the profit margin. From the government perspective, I can actually do that day in and day out, and have done ever since Colombia, in fact. So this whole chart, that I just showed you, and my discussions around the world have focused on doing that, which is to actually tell people what we have learned throughout our spaceflight history. I've gone to companies that are involved in flying our next astronauts, those being companies like SpaceX and Boeing. I've been to the suborbital entrepreneurs such as Virgin Galactic. So I've been to both London and to the Mojave Desert Center, where they do their flights from. So far, if we include the story about how Columbia broke up and what happened to the crew and the crew module of Columbia, so far we've reached about 70,000 people, and that number continues to grow. As, by the way, does the number of boxes on that chart. We learn from every single human spaceflight that we have that this is certainly a risky business, and one in which accidents will happen. And I have no doubt that number of 21 in terms of fatalities in human spaceflight will grow. Maybe not in my work time or my work life, or maybe not in my lifetime, but it will certainly grow above that 21, because we're all involved in basically the exploration of space. So hopefully I've whetted your appetite and tried to tie together the risks that I've faced every day, or the risks that I have to manage every day in terms of putting people on board spacecraft that launch with 7 million pounds of thrust underneath them, and what may seem like the lesser risk to your patients and to your staff in the everyday world that you actually work in and you function in. There are risks that are common to all of us, and managing those risks is key to actually being successful in all of our endeavors, including mine. So with that, I'd like to thank ASPI, and I'd like to thank Dr. Perver for the invitation to come and talk to you today. It is with some sadness that I can't be with you in person, since when I visited Belfast about 2 years ago, I instantly fell in love with both the people and the city. So I hope over the next 2 or 3 days, if you're not from the Belfast area, that you'll fall hopelessly in love with that city and the people as much as I did. And with that, I'd like to thank ASPI, and I'd like to thank especially Dr. Martin Duffy for being my host 2 years ago, and for arranging this interaction with you folks there. And with that, I'd also like to open the floor up to any questions you might have.
Thank you, Nigel. So we have 2 roving mics down the aisles, so if people want to ask questions, or sorry, 3. Maybe if you'll indulge me, Nigel, the last time you were with us, after your address, I then had to tell you that your phone was about to light up because a Soyuz launch had aborted after launching, but before getting to the space station. I'm glad to report that on this instance, I don't have any space-related news to give to you.
Well, thank you so much, Martin. I really appreciate the fact that I'm not called away unexpectedly.
Very good. Looking for some hands if anyone has a question for Dr. Packham. Dr. Hyam?
Nigel, thank you so much for taking the trouble to talk to us and to use technology to enhance learning today. It was a really interesting session. So my question really relates to learning from error. And of course, what we see in NASA is a resource-rich group that thinks very carefully about error and about what to do to prevent it. What advice do you have for the resource poor NHS? Any golden nuggets for us?
Well, I would, first of all, let me back up a second. In at least 4 of the incidents that I showed you the photographs of, both Apollo 1, Challenger, Columbia, and Soyuz 1, I would say that we may think carefully, but I would also point out that there are other contributing factors that are completely non-technical and over which we have very little control, and that is the management side of the house. So there are pressures from the outside to undertake these endeavors and to undertake them at certain times, and the most obvious one there was the Soyuz 1 launching when it certainly wasn't ready to launch, and everybody knew that it wasn't ready to launch, but it launched because of political pressure anyway. But I would tell you that in the other 3 accidents there was significant management involvement in those accidents. And I'm sure that some of you may understand or may have seen J.B. Reason's Swiss cheese model of accident causality. So that it takes all of the holes to line up in that Swiss cheese model before that accident actually happens. So that any one of those, if you can rotate that Swiss cheese layer or that slice, you can actually stop the accident from happening. But let's say that it has, and which I think goes to your question. Remarkably, I would also say that there are not as many resources that you might think that are here within NASA, although we can call on anybody that we need within academia and industry. What I would say is invest the time in specialists that look at the causes of those accidents. Martin Duffy said that I was involved in leading the analysis of the Columbia crew survival accident or investigation. That was a remarkable effort on the behalf of a very small team of folks. I had 7 people on my team that worked basically after hours, on holidays, on bank holidays, 3 o'clock in the morning, 4 o'clock in the morning. One of our recommendations from that whole effort was that in the event of an accident, you need to have people that are given, the only task that they are given is to find out what happened. So if you are resource poor, you still have to be able to designate individuals as those individuals that will investigate that error or that accident until it comes to the point where you've asked all of the questions why, right? So that's to get to the root cause. That's what you have to do, is you keep asking those questions why. And when you can't ask any more whys, then you've probably got the root cause, or at least you've got the proximate cause. But allow the luxury, if you want to call it that, of having those individuals that are dedicated to finding out exactly what happened in that particular case.
Okay.
Hopefully that answers your question.
Another question from the back.
Thank you very much for that excellent talk. And importantly, we do need to focus on when mistakes and accidents happen. I just wonder if there's any focus on human space endeavors on when it works well, whether the investigations into that or what we refer to in the healthcare industry as safety 2. So just interested to know your opinions on that.
Absolutely. We have multiple lessons learned databases here at NASA, and I'm saying that because I know, because we've been talking about it over the last 3 weeks about how we can improve it. The lessons learned database is not only about bad things. It's when things go well, how do we capture that? After every mission, we sit down with not just the crew members that were on board the vehicle, but the ground controllers, the engineers, the managers even, and say what worked well and what didn't. We go through formal debriefs of the real space crew and say, you know what, we estimated 2 hours of time for that particular procedure. You called down and said it took about 3.5 hours. So what can we do better to estimate how long that might take? So lessons learned databases are not only for when things go wrong, but actually when things go right. I should say, though, that lessons learned databases are only as good as when they're actually used. You can learn lessons, you can capture lessons, but whether or not you learn from those lessons is up to the person that actually is doing the work. Hopefully that answers your question.
Okay, thank you. Any other questions for Nigel? While people are thinking of their questions, Nigel, can you give us a snapshot for what simulation might be going on today in the Johnson Space Center?
Well, I actually looked at some of the television cameras over in our flight control rooms, and we have 3 or 4 flight control rooms, one of which is the International Space Station flight control room that is staffed 24/7. And I should tell you that, well, let me put another quiz out there for you. So, how long do you think we've had continuous human presence in space on the International Space Station? So, hands up if you think it's been 5 years or more. 10 years or more. I've got one hand, oh, a few more, okay. If I told you that we now, as of last week, we have had a continuous presence in space on the International Space Station for 19 years. So we have gone without having people, we've gone without not having people, that's a double negative. So people have been on board the space station continually now without any break at all for 19 years. So what's coming up in the simulations? They're probably simulating some of the next flights that are going to happen with crew members on board, which may or may not be actually a NASA mission. It may be a SpaceX mission. So SpaceX and Boeing, who are our 2 commercial partners in our commercial crew program, which will launch both US astronauts, NASA astronauts, and individuals from their companies within probably the first quarter, certainly before the middle of next year, on their spacecraft. So they are simulating right now what one of those launches might actually be. In our simulations, we don't just simulate the procedures and processes that would happen normally. We actually throw very bad days at some of these flight crew control teams. So we actually dream up some of the nastiest things you could possibly think to throw at these control teams to see how they would handle it. Mainly because it's better to handle in the simulated environment and to get it wrong and to learn from those experiences than it ever would be if you did it for the first time when it's real time. And I will tell you that landing on the moon, Apollo 11, they simulated the error messages that were flowing down from that Apollo 11 spacecraft. The computer was being overloaded over and over again. They had simulated that on the ground, and on the ground, the first time they did that simulation, they actually aborted the mission for no good reason. The error messages that they were getting in no way, shape, or form actually precluded them from landing. But had they not simulated it, we would not have landed on the ground on the moon in July of 1969, and perhaps not even after that.
Okay, there were some questions from the front.
Yeah, hi, I was really interested in watching the launch and the thousands of people watching in the video cameras, and going back to your point about political and social pressure. Sometimes working in operating theatres, we suffer from production pressure, and whether we should continue with the skill mix or with the equipment not working, or to continue or not, and the pressure that we're under. And I'm wondering if you've got any advice for us having to cope with that huge amount of social and political pressure to meet targets and deadlines and carry on, and how we can remain safe, and strategies to avoid making the wrong decisions with that amount of pressure.
Well, that's a panel discussion we could have for the next 2 hours. By the way, I should let you know I come from a medical family. My father was a urologist. My My mother was an ophthalmologist, and my brother just retired as a general physician. So I know all too well the pressures that are involved in the operating room. I used to watch my father operate quite a bit, which today is probably wouldn't be heard of anymore because of liability concerns. But political pressures, my brother related to me on many occasions that the politicians were essentially dictating to him how many patients he had to see in a day, and what, if any, prescriptions he could actually prescribe to that patient, or what course of action he could actually send that patient through. Especially in an environment, as you say, where budgets are tight and equipment is malfunctioning. I will tell you that the same building that I'm sitting in right now, it was probably constructed over 40 years ago. The original mission control room from the Apollo flight control room, which has just been renovated, was built back in the 1960s. So it becomes very important to come up with innovative ideas within the restrictions that are imposed by those political and sociological boundaries. But I would also say that our job here at NASA's Johnson Space Center in Houston, which is the home of the astronaut corps, is to keep them safe. That is our mission. And I would put it to you that your mission includes keeping your patients safe. And we've had political pressure being put on us to launch in a certain time frame, but we've also had the accidents that severely impacted our normal course of business. Each one of those accidents, certainly Challenger and Columbia, was followed by 2 years of non-flying. So if you have accidents like that, which was certainly preventable in each case, then you will have to deal with the result, which in our case was not flying for 2 years. In your case, loss of human life is also something that is certainly not something that we want to have happen, and incurs a lot of post-event issues for both you and your colleagues. One thing that we've done since Columbia, I should tell you, is we have strengthened and broadened what we call our dissenting opinion process. In current day, if we have any individual that feels that a design is not safe, or the launch of a space vehicle with people on it is not safe, that they have the right and responsibility to stand up and tell us that that is not so. And they have the right to appeal that decision all the way up to the NASA administrator. So, and this is not somebody in my position as Associate Director of Safety. This can be an entry-level engineer who may, by the way, have more information than I do about a specific technical subject, that they have the right and I would say responsibility to raise that dissent and to appeal that dissent all the way up to the highest levels to ensure that the right decision is being made.
Excellent.
Hi, thank you very much. What you were referring to there sounds like a very active step forward in the culture within the organisation in terms of listening to the more junior, less experienced, less senior members of the team. And I think that's something we're very much trying to instill and sort of shape in the culture in the NHS in recognition of obviously the importance of that in incidents and also safety going forward. So how have you managed to actually make that work? Because we find that there may be a cohort of people that are on board with that approach, but changing people's behaviour of all different ages and levels of experience can be really challenging.
Changing human culture is very difficult to do, but I would say that it starts at the top. If in my case, the NASA administrator says that this is the way it is going to happen, and if you have any issue that points to there being an increased level of risk to the point where you believe that mission is not safe, then you need to come forward and tell us. I will tell you, my father who passed away in 2001. As I said, I was observing him in the operating room, and I will tell you, even back then, the consultant surgeon in an operating room was looked at as the person in charge, and it was very difficult to challenge that person, purely from the cultural perspective. I would like to think that it has changed a little since that time in the mid-70s and to the mid-80s. But I would agree also, and I'm being very honest with you, I would agree that it is very extraordinarily difficult to change the culture of an organization that has one individual in charge of the actual mission, or in your case, in charge of the operation. But I think stressing the fact that it takes all members of that team, for example, a surgeon cannot do the job without an anesthetist, and cannot do the job without the scrub nurse, and cannot do the job without the janitor who comes in and cleans that OR to ensure that you don't have infections making their way throughout the entire facility. There's a famous quote by one of our ex-administrators going through a facility down at the Kennedy Space Center, and he was talking to one individual and asked him what he did. And the gentleman said, I helped launch the space shuttle. And later on, it turns out he asked one of his aides who that person was, and it happened to be the janitor. If you can get to that culture where every individual in that organization is appreciated for what they bring to the table, then I think you've made a huge dent in the philosophical approach that was the mid-70s, mid-80s.
Okay, we have a question at the back in the middle there.
Nigel, I have more of an observation rather than a question. In a sense, I've been invited along to the ASPE conference as a service user, someone who has mental health problems. And maybe I'm like the janitor in the room. And I've been very interested in what you've been saying, although I don't understand the technical aspects. But I just find that when I tried to keep myself safe by not taking risks, I was a very sick man. But I'm learning to take calculated risks in order to experience healing. And really, as I say, it's just an observation rather than a question.
So this must be Bill or Will, is that correct?
Bill, yes.
Well, good evening, Bill, and thank you for being there. I know that the patient side of the equation is always extraordinarily valuable to have. I think, first of all, I commend you for taking those risks, but I think you weighed those risks, right? You managed those risks, and it's a risk versus risk trade again. For example, if you hadn't taken those risks, you would have been worse off. By taking those risks, you are in a better position today than you would have been had you not taken it. And that's exactly, I'll be honest with you, Bill, that's exactly what we do here. There is a risk of losing a crew member or losing a friend when they get into a space shuttle or a space vehicle. The question is that risk, have we truly identified all the pieces and all the components of the risks, the risk that is going into that overall mission? And do we think it's worth it? And in every case, we would not go forward if we didn't believe that risk was worth taking. And I think what I'm hearing in your voice, at least, is that you paralleled exactly that. You believe that the risk was worth taking for your own health. So I commend you for having taken those risks. Thank you, Bill.
And thank you, Nigel, for understanding exactly what I'm trying to say.
Okay.
Thank you. I don't see any other hands raised, and I understand it's hard to top that, Bill. I think that's been a really positive contribution, and I think a fitting way to end our Q&A session, if everyone agrees. I'd like to end by thanking Nigel, and also to thank you, Bill, for coming, joining us and making that contribution. Thank you. So, Nigel, thank you so much for your time. It might not shock you to hear that here in Belfast, we're all going for drinks. I'd like to draw this session to a close, and we'll join you all for chat and some drinks after. Thank you, Nigel.
Thank you, Martin. Thank you, everyone.